What you are just seeing is basically the stochastic, nonlinear, dynamical equations that we discussed at the very beginning of our conversation. What you're observing here, it can be called as collapse dynamic. This is literally collapse of the wave function that you guys are observing, a random jump either to the up or to the down, or you can call it a continuous measurement, continuous monitoring of a quantum system. For almost every field of research, it is as if you're standing on the shoulder of some experts. An expert on PDE, an expert on geometry, an expert on geology, an expert on nutritional sciences, and all of them in a coherent system. God knows how much resources it has taken from Wolfram research, but we have to make sure that all these different ideas, they work in a seamless way together. Borrowing the words from Stephen Wolfram himself, he always says what you have to do in a mathematical notebook is running computational experiments. It's literally an experiment that you are doing, but in a computational way.
So thank you very much for agreeing with this quick talk. By seeing at your career academic background, I saw that you work a little bit with quantum computing. Actually, in 2016, I saw that you worked in a joint project with Google, Berkeley, and Riverside, right?
Mm-hmm.
Can you share a little bit about that? How was that kind of trajectory related to your background and in this quantum computing side?
For my graduate studies and also my PhD, I work mostly on a very particular dynamical equation that we usually refer to them as collapse models or nonlinear stochastic Schrodinger equations. So these are dynamical equations developed in the 80s, 90s by a couple of Italian American physicists to describe the collapse of the wave function. Okay. So instead of postulating the collapse, you have a dynamical equation describing them. Fast forward, with, more technological advancement in measuring and controlling quantum system, experimentalists, they learn how to monitor quantum objects in a weak way. This is what we usually call as continuous quantum measurement, which means as you are monitoring your quantum system, it doesn't collapse to spin up or spin down. It can be literally anything. And in these scenarios, you can do lots of interesting things. For example, these are the scenarios that you can simultaneously measure non-commuting observables. These are the things that are not doable in the case of collapse scenarios. It turned out the dynamical equation for these new experiments is exactly the same as those, fundamental, description of the collapse model. So I don't know how should I describe it, pure coincidence, or there is a deeper meaning into that. I believe there's a deeper meaning into that, but anyhow, so I had learned, about those tools, and I had the opportunity of applying them for a very interesting topic, which was basically doing Shor algorithm in a stochastic way, and the rest was the history.
Oh, that's nice. When you say that they do not collapse, and can I say that they stay in a superposed state?
In a sense, yes. So basically, it's that's why it is called weak measurements. Okay, so it's you are not measuring your system strongly enough to have a very specific spin, and because of that, you are not sure what's going on. Or in the case of Steinerloch experiment, it means when it passes through the gradient of your magnetic field, instead of putting the detector far enough, you put the detector too close. So the two beams, they do not have enough time to get separated. So when you get spin up or down, you are 100% sure. If you measure it somewhere here, you are kind of halfway, sure, meaning it's a weak measurement. So these are very interesting scenarios with lots of application for quantum computing, because at the end of the day, all these systems as of now, they are very noisy, and whatever computation you want to do, it should be done including like, this randomness. And since I knew about that, like, I basically used those skills for this very interesting problem.
That's nice because it's common knowledge that this kind of environmental noise can disrupt the, so to say, the properties that makes like a quantum system operable as a quantum computer, for example, right? So as far as I understand, this kind of weak measurements that you're mentioning is like you're measuring, but you're not perturbing the system enough, so it would collapse to a single state, and then you will not lose that kind of superposed states that are required for quantum computation. Is that accurate?
So basically, like, using quantum systems for any computation, the biggest challenge is their sensitivity to any environmental noise. Because that quantum advantage, if any, comes from quantum superposition, quantum coherence. And quantum coherence is very sensitive to any decoherence effect. And either you have to isolate your system in the best possible way. That's why, like, many of, like, these quantum systems, they cool it down, very close to the absolute zero, or you have to find, like, other ways such as quantum error correction, because whatever you do, eventually some errors happens, and then, like, you have to correct them. There are, very active field of research, like, what are the good states, like, magic states, etc., that are, like, good candidates, and, like, what are the best, error correction scenarios, which is actively pursued by many scientists.
That's nice. And changing a little bit of topic, but when was your first contact with Wolfram Mathematica or any kind of mathematical Wolfram tools?
I remember that exactly. So it was like,
Really?
during my master degree, and we were studying, like, simple double slit experiment, the quantum version of that. And I had this very good friend of mine who is also a researcher right now. And I was explaining, showing him, like, this the equations that I had drive on pen and paper, like, hey, look, this macromolecule passing through, like, this grating, and then, like, etc. This is the interference pattern, blah blah. But of course, it was very abstract, raw pen and paper derivation. And this friend of mine, he was a, like, a very good mathematical, like, developer, and he told me, hey, look, give me your equations, give me, like, a couple of minutes. And then he, wrote all the codes, fancy codes. I had never seen Mathematica before on that level. And then, boom, we evaluated that, and we saw the interference pattern. And I remember the magic. For me, it was really like, a magical moment. Like, that's exactly what we observed in the experiment. Like, I have seen, like, exactly the same pattern, like, from the experimental data. And that was the beginning of, let's call it, my love story with Mathematica and Wolfram Language. Since then, I become, like, a user, and on day-to-day basis, I have been using that for many different things.
That's a fantastic story because I can see that it really marked it. Like you remember the day and the feeling when you saw that kind of patterns, interference patterns
Mhm.
in the spring. It was really nice. And I have another question related to that because after that, after your master's, I know that you pursued like your PhD and then
Mhm.
you were a postdoc for a few years.
Yeah.
But I saw that you were, I think it was in 2018, you were the academic director of the Wolfram Summer School, right?
Yeah. So,
How was that experience?
yeah, what happened was that I can tell you, like, typically, like, in academia, like, there's a relatively, like, a very clear trajectory. Like, it's like your professional development is like, if you want to stay in academia, like bachelor, master, PhD, couple of postdocs, and then you would join, like, as a faculty member somewhere, depends on where you want. And you would start working on different topics. That was what I did. But very soon I learned that, like, at least academia at that time, it was, for me, it was kind of like, limited in a sense that, like, I was interested to work on many different topics because, as I said, when you learn about a tool, you can apply that tool on many different topics. Okay. For example, the same models that we have for chemical kinetic, it can be used to study the spread of a disease. Okay. So it's the same dynamical equation, exactly the same model. So somebody who knows chemical kinetic, they can also study, like, the spread of a disease. At least at that time, like, academia was not very welcoming to switching the topics. So if you are in math department, you have to publish about math. If you're in the physics department, you have to publish in physics, chemistry, likewise. Um, I really wanted, like, to have the possibility of this switching between many different topics, like, do this, do that, like, and I wanted to pursue, like, my uh, passions more seriously. I was very lucky that, like, I went to the summer school, and I was like, I met Stephen Wolfram himself, and he offered me the job. And then I joined Wolfram Research, and then I started, like, working on many different, projects, including Wolfram Summer School. That was my entry point to, Wolfram Research. And I also highly recommend to anyone. This is one of those unique experiences. I'm sure, like, you also, Lucas, you are coming from the same experience. Like, it's so unique and different from other educational experiences, and, like, it opens up a new horizon. And since then, I'm pursuing that professionally and very seriously.
That's amazing. That's indeed a very um, nice trajectory. And also, the summer school has this kind of effect in people. I can tell that you get amazed about this experience of 3 intense weeks of 100% focus on developing your work and overcoming a lot of things to get things done. And at the same time, there's a lot of networking. You meet a lot of people from all over the world, and it's amazing. It's fantastic. But when were you in the summer school as a student?
So, gosh, now, like, many years ago, if I'm not mistaken, like, 2018, I was, officially the student. And then since then, I have been, when I joined Wolfram Research, I have been part of, like, faculty member, director, etc. And very happy to see that, like, recently we passed the torch to the next generation. So now, like, like, other alumni of the summer school and other, like, colleagues at Wolfram Research are basically moving on with the same mission and with the same, passion about summer school.
That's amazing. Let's talk a little bit about what you do like daily in your day job
Mhm,
in Wolfram. What kinds of questions are you usually responsible to in your day job, for example,
mhm.
at Wolfram?
So, the biggest umbrella is quantum. Okay, so that's my expertise. So basically, any question, anything that is quantum related, I am the person who is responsible for that. Uh, and that covers many different things. Like, of course, like, more recently, recent years, quantum computing is kind of dominant topic with lots of uh, technology and hardware development. This is, like, the area that many companies, academia, they are, and governments, they are pursuing that very seriously. So we are offering help and our technical expertise at many different levels, from education all the way to basically hardcore development. So these are the sort of things that, like, more recently I am mostly involved with, like, quantum related projects.
That's nice because something that I like to ask you is we have seen a lot of news because we have, for example, blockchain technologies that are very reliable in terms of transactions and cryptography and something like that. And I have been seeing a lot of news that quantum computation has the potential to overcome blockchain technologies if it's really show that it's doable and it's actually it's doable on a large scale, so to speak. What do you think about that?
So when we talk about quantum, we have to remember a couple of things. So, number one, in terms of theory, this is basically the most sophisticated mathematical framework developed by humans in the history of humans. So, and it's been well tested, one of the most beautiful theories that we have. That said, it has lots of open questions too. Okay. One of the biggest questions at the foundation of science is uh, the connection between gravity and quantum. Open question. We don't know what's the solution. Some people would say we have to quantize gravity. Other people would say we have to gravitize quantum. Which direction is the right one? Nobody knows. So this is one area that, like I'm talking about very foundation. Okay. So like quantum is like at the frontier of one of the most important questions that we have about nature and how nature operates. Then this theory has lots of different applications, for example, in quantum chemistry, in designing new material, in sensing, quantum sensing. Last but not least, quantum computing. Everything that I said in terms of application, it's happening and it has been happening for a couple of decades. And we are seeing more and more technology coming out of different, quantum features. Like the laptop that is in front of me, the cell phone that we are using, these are all byproduct of quantum revolution, or sometimes people, they would refer it as to the first quantum revolution. So it's been ongoing for more than 100 years and it's happening more and more. But that's not what people usually hear nowadays about quantum. Nowadays, most of the time when people talk about quantum technology, is about the second revolution, which is related to basically quantum computing, using quantum systems for the sake of computation. And at least on paper, it's been proven that it can provide much better performance compared to any classical hardware classical algorithms. This is the area that's it has huge potential. There has been huge advancement. We are not there yet. Okay, so I remember when I was a graduate student back in 2010, they were telling us, oh, the next 5 years, okay? If you go to any scientific gatherings nowadays, they would still tell you the same thing. The next 5 years, you are gonna have it. You are gonna have it. There has been, again, don't get me wrong, lots of improvements, lots of advancement. We are not there yet. So, one thing that I want everyone to remember is this: there has been lots of technological advancement because of the quantum, and they are there in our day-to-day life. But quantum computing, which is kind of the elephant in the room, is happening slowly. And the past few years, there has been lots of good improvement.
That's nice. And what are your views on what's gonna happen? If you have to guess, what would you think that's gonna be like a great advancement in terms of quantum computing for the next 5 or 10 years?
I think the area of microelectronics and quantum, we are gonna see lots of improvement. This whole AI chips, etc. Even not fully quantum. These two field of research, they're gonna learn and they're gonna interact much more, and it's already happening. Even uh, last year, Nobel Prize in physics. If you look at those three awardees, all of them right now, uh, they are working together with these chip manufacturers, and there's a very close collaboration between them. So microelectronics and quantum, we are gonna see lots of advancement. Does it mean we are gonna have quantum computer? I think we know we have to be more patient. Okay. uh, then there are many different modules. Okay, we have ions, atoms, superconductors, photonic systems, crystals, etc., etc. Which one is gonna be the winning modules? It's very hard to predict, and that goes with any new technology, because performance in one thing in tech, but providing that with a reasonable price is another factor. Okay, so these two, they should kind of come together. Um, so it's really hard to say, like, which one. I think, like, all of these modules, like, we are going to see more improvement. And if anything, I believe the first impact is going to be the integration of these quantum processing units, QPUs, and high performance computing, like, facilities. So quantum and HPC, I think this is the area that we are going to see the very first impact.
That's great. I was gonna make a joke that people want personal quantum computers, like, like today, please. But I understand that this is something that is slowly progressing, and it's not about like scalability at the point. It's about making it work and is actually use it to solve problems.
True.
And in this sense, would you share with us like some project that you are working right now, like that you have been working on this, and it can be something that is published or not published?
So, like, one thing that I would like to share right now, which is related. Actually, let me tell this story, and then, like, I'm gonna share my screen and I'm gonna show it to you guys. Like, uh, at Wolfram Research, the main thing that we are producing is a computational tool. Okay, so basically, we are giving people a very unique tool that can help them to do any sort of computation in any field of research. And this tool is so unique that, like, and uh, I personally like it a lot. Uh, so we are tool maker in a sense. What is special about this tool? If you talk with people who were, for example, in academia or, like, in doing, computations 30 years ago, they would have a very clear idea. They can tell you about their personal experience with our product, Mathematica and, Wolfram Notebook. 35 years ago, around 35 years ago, like, all of them, they experienced that wow moment. They were like, "Ah, you can solve some dynamical equation. You can solve integral." So that was like the wow moment, the biggest impact of, like, our product. And it changes everything. It was really, like, a turning point, like, in doing research. That wow moment, maybe for the new generation, it's kind of gone. So if you tell them, hey, there is a software that you can do very fancy integral or very fancy computation, they'll, yeah, okay. So uh, uh, this is still one thing that, like, at least for the new generation, it's gonna take time to understand, like, the wow factor that is there. That said, now I'm gonna share my screen and I'm gonna talk about, like, another, product that we have had, and the wow factor is still there. And that product is simply basically the environment that you see. It's an integrated environment, which is basically like, a mathematical notebook. This is a technology that was developed 35 years ago, or even more. And I can tell you, even today, there is no counterpart to that by other companies. So it is so unique. And this is the thing that I always want to tell people, like, even working with this within this environment, the whole concept, it's gonna give you that wow factor. It's very similar, like, you can think about it like this, like, sitting in a very fancy car, okay? When it drives, even the noise of the engine, and, like, say, wow, okay? Or when you see a very, like, beautiful jet fighter, it has the wow factor. Like, wow, like, look at that, how beautiful it is. So this environment that you can type text, you can run code, you can solve differential equations, uh, you can have visualization, you can do God knows tons of other things, like, connect with, like, other environments, send a query to, like, an AI bot, or send a query to a quantum processor that is on cloud, connected via cloud. It's very unique. Okay, there are some mini version of that in other platforms, Jupyter Notebook, etc., etc. But what we have here after 35 years, it is still magical. And I really, like, motivate everyone. work in this environment to understand the magic of this integrated environment. An environment that you can have text. It's like really literally like a word processor, but you can have code. You can do simulation, etc. So what you see here is a small portion of a book that I'm working on, which is about qubits, the simplest quantum system that we have. What I wanted to show you guys is basically what I did for my PhD, what I did for a couple of my postdocs. What I can tell you that I understood it when I really ran a simulation like this. So let me just I want you guys to look at the trajectory of these arrows. And then on the right side, we have basically the histogram of distribution of those arrows. Let's just run it. Just let's look at that, what's going on.
Wow.
So you see some of those arrows, they are rotating. All of them are rotating. And then in a random, movement, they are going toward North Pole and the South Pole. And it seems the histogram, the distribution has reached kind of a very limiting case. Okay. So what you are just seeing is basically the stochastic nonlinear dynamical equations that we discussed at the very beginning of our conversation. And this is basically what you're observing here. It can be called as collapse dynamic. This is literally collapse of the wave function that you guys are observing, a random jump either to the up or to the down. Or you can call it a continuous measurement, continuous monitoring of a quantum system. As I said, both of them it follows the same dynamical equation. And it has lots of interesting features, martingale, feature. What's that fancy term? It means for a collection, large enough collection of these arrows, the distribution is gonna reach what we predict by quantum theory, which is simply Born rules. Okay. I personally learned that when I did a simulation like this. Okay. So it's just, I can tell I had seen the dynamical equation before. I had done all those derivation, etc. But the true meaning for me happened when I did the simulation.
So it's like visualizing the equation, right?
Exactly. So for me, it was like, I learn if I can compute, because when you're forced to compute, you're gonna learn tons of things. For example, let me just show you, our dynamical equation depends on many different variables. And you have to play around these variables to understand that, okay, this fancy Ito stochastic dynamical equation with all those variables, within this regime, we are going to see Born rule. What if I go outside of that? Okay, you're not going to see the Born rule. And by the way, what you see here, it may look very simple, okay? When you look at that, you would say, okay, it has gamma, r that depends on time, theta that depends on time, omega y, etc., etc. What you're observing there, it's doable only in Wolfram Mathematica, because this is what we call as a symbolic approach to your dynamical equation. Okay. I'm not specifying what is gamma. I'm not specifying what is phi. I'm not telling you what is omega y. I'm just saying that this is omega y, exactly the same way that we write it on paper. And Mathematica is among very few that can do symbolic computation. And in fact, the extent that we can do symbolic computation, there is no counterpart out there in the world. So we have the most complete, basically, features to do any symbolic computation. Here, I'm just showing you some examples from physics and math, but that goes to anything. That goes to geography, I don't know, nutritional sciences, just name it.
That's amazing. I have just a quick question about the blocksphere you showed. Because as you run that calculation, I could see that there is a higher weight to the 1.00
Yep.
component of the block. But this is because of the initial condition, right?
Yep, exactly. You see,
Yeah.
the initial one is more biased toward, the top one. So this is the undergrad quantum. So if I give you this initial quantum state, okay, this vector, you would say with the probability of like, I don't know, in this case, I have to remember what I put there. I guess like, it's 65 and then 35. You can calculate that like, according to the Born rule, what are the probabilities? And there is a dynamical equation. Again, this is the thing that I want to emphasize. We are not postulating that there is a dynamical equation that can reproduce basically Born rule.
That's amazing. I have two quick comments. The first one, I think that's this symbolic part of Mathematica is it's really amazing because when you put an equation like in a I don't know, in any computing language, you have to type in so specifically that it loses, like, you cannot see the equation anymore. You just see a bunch of symbols that if you think hard enough and if you look hard enough, you can see the equation. But it's different than actually, as you said, seeing the equation as you would write in paper.
Mhm.
And a quick question is this example in your one of your books about quantum computation?
Yes. So like, I'm working, I'm almost done with the book number one, which is Introduction to Quantum Computing. And then the second book is about quantum information and sciences. And in the second book, like, you can find that example. So toward the end, when we discuss open quantum systems, which is again, like, that's how, like, it relates to quantum computing, because any quantum object that you use for your computation, it is interacting with the environment. In a sense, it's an open quantum system. So your dynamical equation is not Schrodinger equation, it's something fancier, and depending on the interaction with the noise, you have to come up with your dynamical equation.
That's amazing. That's really beautiful. As you mentioned, like, we can see what's going on. Like, it's almost as if we were running an experiment.
Mhm.
Just say but we are looking at the experiment and see that's what's happening. And I know why it's happening because of this equation, this initial condition, these parameters, and so on. So it's really amazing.
I think, like,
And
borrowing the words from Stephen Wolfram himself, he always says, like, what you have to do in a mathematical notebook is running computational experiments. It's literally an experiment that you are doing, but in a computational way.
yeah, and I heard one of his quotes that he one of the things that he likes most in mathematics is because he can compute as fast as he thinks about code.
Exactly.
So
Exactly.
it's really nice.
Very nice
And
saying.
something that you said earlier about the notebook from Mathematica, for example, because it can be used for making notes, of course, but it can also be used for other kind of stuff. For example, I always like to have like an iPad or something like this so I can make notes. And then I'm watching a lecture and then I take a picture of the lecture and I put in the notes. It's kind of this dynamics of studying. And the notebook from Wolfram Mathematica enables that in a very, very nice way. And because as you mentioned, you can write text, you can do computation, you can do calculations, you can make demonstrations. And that's why this whole new concept of Wolfram books, they're really nice because they are interactive.
Yeah, true.
It, this is something that's really beautiful because you can interact with the book.
Let
And
me just, show you, like, another example. Like, this is basically the notebook of, like, the book that I told you, like, Introduction to Quantum Computing. And you see, like, as I'm scrolling through that, it's almost the same, like a Word. Okay, so it's like, oh, table of content, different sections, etc. But as you mentioned, like, you have the possibility of including code. You can run your code, like, you can have, like, in addition to your code, you can have visualization. And then for that visualization, you can have, like, fancy computation. You can, like, find, like, your quantum state, etc., etc. So uh, this is very unique. I can tell, like, I know there are other platforms with similar features, but the level of support and integration that we have in Wolfram Notebook, uh, no comparison. This is still the state of the art of computational notebooks. And it's very funny that it was invented close to, 40 years ago.
yes, and if if you look back in your career, you think that Wolfram language or the Wolfram notebook or Wolfram Mathematica in general, it helped you more to think about problems, execute them, or both?
I can tell, like, whenever I have tried to simulate or reproduce anything in Mathematica, I learn about that topic more for a very simple reason. Like, the people in Wolfram Research who develop those functionalities, they are the domain expert, okay? Somebody who has written, like, functions to solve, I don't know, a PDE, a partial differential equation. That guy was an expert on PDE, okay? So the design of that function force you to define your problem in a systematic, correct way. Okay. For example, you go to NDSolve, you put your function, you evaluate that. You're like, what the heck is not evaluating? Bunch of errors. You would say, huh, I gave everything. What's going on? And then, like, it forces you to design your problem in a scientific way. You look at your equation and say, oh, now I understand. There are some assumptions in this dynamical equation that are implicit. But if I want to simulate that, I have to be very explicit about it. Such as what? Am I doing the simulation in a real domain or in a complex domain? Am I giving that a very specific assumption? For example, this parameter is integer. This parameter is always positive. This parameter is this and that. These are, like, very minor, subtle details. But the moment that you want to basically simulate that, you have to pay attention to all these details. And this is a moment that you would say, now I understand it. All those footnotes or kind of implicit things that are not explained properly in a paper or in a textbook, when you want to reproduce that, you have to learn it because it's literally like an experiment. Okay. You're running an experiment. Therefore, you have to pay attention to every single detail.
It's really beautiful, this what you're mentioning, because it's a mixture of learn by doing, and at the same time, you have to. I really like that you mentioned that because we didn't talk about the built-in functions, but this is another amazing feature of Mathematica because each of those built-in functions have tons of code behind it in the background, and it's when you're gonna use it, you have to pay attention to these details, and by doing that, as you mentioned, you learn in this process. It's not just a code. It's not just something that you have to memorize and type in to do something. It's a structured structured design code that it's already built this kind of thinking, and it's really beautiful.
No, true.
And
And this is the area that, like, especially for students, I highly recommend them, like, be patient, read the documentation, and learn how to use these functionalities. I know, like, there are some details, like, uppercase for the building functionalities, like, how to give an input, how to introduce assumptions, etc., etc. These are minor things, but they are very important when you're describing those assumptions. Like, you will be surprised in some problems how important are those subtle assumptions. So, uh, as you said, like, it's not just like, learning by doing, it's more than that.
yeah, and talking about this key nice features about Wolfram language and Wolfram Mathematica, you mentioned previously, but this is something that uh, for me, for example, my first contact with Wolfram tools was with Wolfram Alpha when I discovered that there is a website that not only solved integrals but give you like the step by step, and that was amazing because a lot of undergrad and grad students use that till nowadays, and this is really beautiful. But looking back with your experience, what do you see as the lasting legacy of Wolfram Mathematica for both the scientific, the academic, or the uh, technical community?
Uh, I think still God knows for how many more years. The whole concept of computational notebook, it has so much novelty that I think it's gonna last for a very, very long time. Okay, this is fundamentally one of the maybe most original contribution of Wolfram Research as a company to the whole world. Okay, so that concept is there. We still have the best, and and this is something that people uh, they're gonna acknowledge more. Uh, I should say, I believe, scientific community, they should pay attention more to this concept. Not everyone knows enough about, this gem, which is basically the computational notebook. Another aspect is this integrated environment. Okay, what I showed you was functionalities on, for example, physics, quantum, chemistry, etc. Let's say that you want to do an experiment, and or you are doing a simulation, and you need to know what is the geo area of, I don't know, LA, Los Angeles County. Okay. What is the temperature of LAX airport 10 years ago? What was the tide during the D-Day, and that eventful, mission during the Second World War? Okay. All of these details, if you want to find that information on your own using even the most advanced, AI bots, good luck. All of them are built in Mathematica, and not only is there, it's been also curated. And this makes your life much easier. In other words, I always tell people, when you are using Wolfram product for almost every field of research, it is as if you are standing on the shoulder of some experts. Okay. An expert on PDE, an expert on geometry, an expert on geology, an expert on nutritional sciences, an expert on quantum, and all of them in a coherent system. That's the most important part. Okay, so there is no inconsistency between them, because this is one of those things that God knows how much resources it has taken from Wolfram research, but we have to make sure that all these different ideas, they work in a seamless way together. And maybe we are, if not the only one of the few companies in the world that, especially in software domain, that our very, very first product, if somebody has a Mathematica notebook from version 1, they can run it on the latest version of Mathematica. This is something, again, as I said, it has taken lots of resources from our company to make sure that all these things work simultaneously and seamlessly. But this is the unique feature. And we are trying to catch up with all these big changes that is happening out there. For example, uh, nowadays, one of the things that I use myself is, Notebook Assistant, which uses AI behind the scene, because I do not remember all the details. Sometimes I want to do something. Hey, I want to define, I don't know, the boundary condition in this differential equation. How to do that? I go to Wolfram Notebook Assistant, I just type it, and it gives me the code. And I get the code, and I do the rest. So we are also following all these other big changes that is happening in the domain of computation. And I think the future, it's gonna be a combination of Wolfram way of thinking about the world plus this very fancy AI way of thinking about the world.
You mentioned, I can see that you have this kind of vibe that to talk to the younger generations, and this is really nice.
I did my graduate studies and some of my postdoc in Italy, and when people think about Italian culture, you would say food, and how warm they are, and especially food. Okay, but when you think about like eh, as a count, how popular is the Italian language? Okay, like you're saying, we're gonna like Lucas, me and you, like English is not our first language, but we are communicating like through English language, okay? But when you go to Italy, forget about like any other language but Italian. Even if you know a few words, if you just respect those few words, the experience that you are gonna gain is gonna be utterly different. Even if you speak just a few words, and that goes with any other country. If you speak the local language, if you understand the local thing, it's gonna be utterly different. That's the thing with Wolfram. Okay, uh, there is mainstream thing, which is kind of maybe the dominant one. Great, learn that there are always gems, and those gems is not everywhere. Okay, usually the best car in the world, you don't see it every day on the street, right? Like so if you're looking for the best, something unique, you have to look for that. Okay, it's not everywhere. You have to learn, you have to gain something to basically like reach that point. That goes with Wolfram products. I always tell people like it gives you a completely different perspective toward your computation, toward your simulation, to the way that you think about the world. And it at least worth having that experience because it's not, as I said, it's not the mainstream. You don't hear it anywhere else. And it's very unique in our ecosystem. And I'm sure, like, if they are patient enough, they are going to enjoy that, at least as a very different experience.
So it seems that Wolfram capabilities, uh, they are way more um, present than we see them in many things. And of course, we do not expect that Wolfram language or Wolfram tools are going to be broadcast all over the news every day. And so where people are going to start, oh, that's nice. But I think that by sharing on social media like YouTube or making these kind of social events like summer school, winter school, and other kinds of school, this is some way of broadcasting this tool like, hey, you can do this with other kinds of tools, but look at this tool. This tool makes it to solve your problem in a maybe unique way. And this is really beautiful. With this, I thank you very much for this amazing talk. I learned a lot by talking to you. Thanks for agreeing with this interview and for bringing so much nice information and so nice advice here. And I hope that people that are watching this get um, really excited about learning more. And there's a lot of free web course available on Wolfram Language. So thank you very much, Matt.
Sure thing. Thank you.